Welcome back to our little corner on the web, where we go through math problems to hopefully encourage and inspire an interest in math. Today, we will go over questions 9 through 12 of part 2 in the 26 PMO qualifying stage. Question 9. A palindrome is a number that reads the same backward and forward. If a palindrome between 100 and 1,000 inclusive is chosen uniformly at random, what is the probability that this number is divisible by 11? So I always think about probability as counting twice, the number of cases that we want all over, the number of total cases. So here, the total cases, we're basically looking for 3-digit palindromes. So the first and the last digit will be the same. So whatever we choose for the first digit will be also the same as the last digit. So the number of possibilities for the first digit, there's 9 possibilities because we can't have 0, which means that the last digit is defined. So we only have one choice there. And the middle digit can be any digit from 0 through 9. So there's 10 choices. So the total number of palindromes in question is really 9 times 10 times 1, or 90. So that will form our denominator. So if you remember your divisibility by 11 rule, it's basically the difference of the sums of the alternating digits. But here we only have 3 digits. So if I call that A, B, A, the sum of the 2 A's minus the B must be a multiple of 11. So 2A minus B must either be 0 or 11 in this case. We can't get to 22 because we only have 3 digits here. Okay. So we can just go through the cases. If it's 1, 1, that's a 2. That basically 2A minus B is 0. So let's go over all the zeros first, because that seems to be easier. So that will be 1, 2, 1, 2, 4, 2, 3, 6, 3, 4, 8, 4. Okay. And there's no other 3-digit numbers that will give us 2A minus B is equal to 0. So we go for 11. For 11, obviously, the A's have to be greater than 5. So we end up with 616, 737, 858, and 979. Okay, this gives us 2A minus B equals 11. So basically, we have 8 possible palindromes out of the 90 that can give us something that's divisible by 11. So the probability is 8 over 90, or 4 over 45. So the answer here is B. Moving to the next question. Ernest has a jar with 26 identical cookies. He wants to finish the cookies in the jar by eating 2 or 3 cookies each day. In how many ways can he do this? So this really looks to me, for those of you who are familiar with some problems in Fibonacci, this is a modified Fibonacci. Okay. Instead of f of n being f of n minus 1 plus f of n minus 2, this is f of n is equals to f of n minus 2 plus f of n minus 3. Okay, meaning if I was trying to figure out how many ways I can eat 2 cookies, there's only one way because I have to eat 2 cookies on the first day. 3 cookies, I can eat 3 cookies on the first day. If it's 4 cookies, well, I can only go from the second day, right? Or the first day, because so f of 2 is equal to 1. F of 3 is equal to also 1, only 3 cookies. F of 4 is equals to basically f of 2 plus f of 1, but f of 1 is 0. So f of 1, and in this case, is 0. F of 4 is just basically f of 2 minus f plus f of 1. F of 5 is equal to f of 3 plus f of 2, so that's 2. So we can actually just keep adding using this identity, because we can only, but if the last cookie we ate was 2, then we came from f of n minus 2. The last cookie we ate was 3, then we came from a number which is f of n minus 3. So notice that all the units digits are different in the choices. So we can actually make a simplifying step for this problem of just adding the units digit and forgetting about everything else. and just keep adding, because that's probably the fastest way. We could also figure out this recursive function all the way until we reduce f of 26 to something that's just formed by f of 4, f of 3, f of 2, and f of 5. But I figure that adding when you're in a competition scenario like this would probably be faster. So we can also now add f of 6, we'll have a units digit 2, f of 7, we'll have a units digit 3 coming from these two. F of 8 will have a units digit 4. F of 9 will be from f of 6 and 7, so 5. F of 10 will be 7 from f of 8 and f of 7. F of 11 will come from 8 and 9. So yeah, f of 8, so that's 4 plus 5. 12. Here we'll throw away the tens digit, right? So we can just keep going. So f of 14, f of 15. And we will see what units digit we find when we get to f of 26. Again, you can probably do this more rigorously by adding everything that you find. But just in this case, because the choices gives us different units digit, I just didn't try to carry them on to make the addition a little easier for us. We don't even need to calculate f of 25 because we only need f of 24 and 23. So that's the final answer for the units digit of what we want, and hence it has to be A. And if you actually do this using, without neglecting the hundreds and the tens digit, you will indeed find that the sums of what you're adding is 660. Okay. Moving on to the next question. Okay, below is a drawing of a lattice polygon P. It has 16 integer points, points with integer coordinates, basically, on its boundary, indicated by circles. And none in its interior. Okay. The polygon 26P is obtained by dilating by P by a factor of 26. That is, it consists of points 26x, 26y, wherein x and y is a point in the interior of the boundary of P. How many integer points or lattice points are in the interior of 26P? So for this one, basically dilation here basically means we're making the shape bigger. Okay. So if we map this lattice polygon P onto the Cartesian plane, we can map this lower left point here as 0, 0. We'll just make our life easier. So 3, 0 for this point here, 0, 3, and 3, 3. And you'll notice that indeed no lattice points are left except for the ones that are marked. Okay, this will be 2, 1, 1, 2, and this will be 2, 2. Okay, so that will be our original shape. And we just want to basically magnify this by 26x. So you could think of a shape that still has this edge at 0, 0. But now the further edge here will be at some point 78, 0. Which means that the one on top here is 0, 78. And you have 78, 78. Okay, so that is now our outer boundary. So if we count just the interior lattice points, okay, then we have something from without looking at the what we're going to exclude in the middle first. Anything here bounded by 1, 1 and 77 comma 1, and then the corresponding ones on the top, 1 comma 77 and 77 comma 77, are what we want, and then we'll exclude the one that's even way deeper inside. So this one is a 77 by 77 square. So literally, there's 77 squared lattice points in there, including the ones on the line, on the line here that I'm going to mark red, including the ones on those lines. Okay. So in total, without the inner boundary, it's 77 squared. So the question now is, what's the inner boundary? Well, the inner boundary, let's just draw it in red as well, will now be 26 comma 26 here. And here will be 52 comma 26 and 26 comma 52. And again, 52 comma 52, right? So there's actually 27 lattice. It's actually a 27 by 27 square. So we will need to subtract 27 square lattice points, which are on the inner square. So this, again, just by the difference of two squares, is no more than 104 times 50, or 5,200. Okay, so the answer here is B. Okay, which are the number of lattice points that are in here, including the ones on the outer red edge, but not the inner red edge. Okay. So moving on to the next question. Question 12. The real numbers x, y are such that x is not equal to y and satisfies the equality chain that we have shown right there. What is x squared plus y squared? Okay, so we're given x is not equal to y, so we have to keep that in mind as we manipulate this equality chain. So let's see what we can find, because there's nothing obviously that really jumps out here as x squared and y squared, x squared plus y squared. So let's try to see what we can find if we just manipulate that first pair in that equality. So cross multiplication gives us 26x minus xy squared is equals to 26y minus yx squared. So some of you, to some of you, this might remind you of Simon's favorite factoring trick. So let's try it. So 26 times x minus y by shifting that first term over there. And then let's take it slowly from here on out. So hopefully people don't get lost. Okay, so now we can factor out an xy from the latter term. So we get 26 times x minus y plus xy times, well, this one leaves minus y, and the second one leaves an x. So let's flip them so that it's the same form as the first term. So now we have x minus y times 26 plus xy equals 0. We know that x is not equal to y, so this term here is not driving it to 0. That must mean that xy is equal to negative 26. Okay, let's plug that thing into the third term here. We will get that that third term is equal to negative 26 all over 26 minus 676. Okay, that actually simplifies out to, okay, let's say it's slowly. Negative 26 over negative 650. So now it's positive, and it's positive 1 over 25. So that means that this whole equality chain is no more than 1 over 25. Okay. So doing one more round of taking a pair of them, let's take this one here, but now we know the value is 1 over 25. So we can do a cross multiplication. That will be 25y is equal to 26 minus y squared. We just have a quadratic. So y squared plus 25y minus 26 is equal to 0. So if x is not equal to y, then the x and y that we're talking about must be the two solutions of that quadratic. So we're only looking for the sums of the squares of the solutions of this quadratic. Okay, so again, back to the sums and products of roots. We have r plus s, which is going to be our xy that we're looking for, is equals to -25. Okay. And RS is equals to -26. So we're looking for x squared plus y squared. So we square r plus s. So we have r squared plus 2rs plus s squared equals 625. And that's basically the two solutions that we want. But we also know rs is -26. So we have r squared plus s squared is equal to 625 plus 52, which is equal to 677. Okay. And again, as I said, those R and S are basically the X and Y that we're looking for here. So the answer here is C, 677. Okay. Hopefully these solutions are useful and educational. If they are, do hit the like button and subscribe. Thank you for watching.